Quantum computing, communication, and metrology are expected to change the paradigm of information processing and precision measurements by harnessing quantum properties of interaction between matter and electromagnetic waves at the atomic scale. Here we see Google's superconducting quantum computer, an ion trap built at Innsbruck, the photonic quantum processor recently released by Xanadu, and QCOL, which is Europe's project to bring the prospect of quantum communication systems to fruition. Now, there are several key components needed by a quantum processor to surpass its classical counterpart. Photon subtraction can be used as a tool to attain several of these key components. For example, photon subtraction can be used to create exotic quantum states of light, to generate non-Gaussian resource states required for universal quantum computing, and also help in entanglement distillation. The usual single photon subtraction method using a beam splitter is analogous to the application of the annihilation operator on an incoming field, which subtracts photons in a probabilistic fashion with low probabilities of a successful single photon subtraction. We propose deterministic single photon subtraction using a 3-level quantum emitter coupled with a chiral waveguide. The incoming red light excites the atom, which was previously in the ground state, from 1 to 3. However, it cannot de-excite from 3 to 1 because of destructive interference with the incoming field, thereby relaxing to 2 and emitting a photon in the blue left mode. Using this method exactly, a single photon will be plucked out from the incoming field irrespective of the type of input light, given the pulse width is long enough and that the input photon number is not too small for a Gaussian coherent pulse. This process can be used to create highly non-Gaussian states from Gaussian coherent inputs, which are an essential requirement to gain quantum advantage according to the Gottesman-Nil-Pascal theorem. We can see that a single photon has been successfully plucked out in the blue left mode with high fidelity. Similar types of single photon Raman interaction has been implemented in cold rubidium microresonator setups and using cold Rydberg atoms before. We study which platforms would be the best to implement a deterministic single photon subtractor based on the coupling efficiency beta and the chirality Z of different emitter and waveguide systems. The solid-state emitters provide many advantages over cold atoms like stronger coupling. Chiral photonic crystal waveguides can be specifically designed by bandgap engineering with high group index Ng and low mode area to attain higher coupling efficiency. After comparison, we predict that charged quantum dots coupled with photonic crystal waveguides should be the ideal system for an almost perfect deterministic single photon subtractor device.